For the second part of the angular kinetics chapter, we're going to go over angular momentum, and we will describe Newton's first, second, and third laws of motion with regard to angular motion. So angular momentum quantifies the angular motion of an object, describing both the current state of motion and an object's resistance to changing motion. So mathematically, we represent angular momentum with h sub a is equal to I sub a times omega sub a, in which h is angular momentum about an axis, I is moment of inertia, and omega is the angular velocity about an axis. So angular momentum is a vector quantity, meaning, again, it has magnitude and direction. It has units of kilograms times meters squared over seconds. And the direction of angular momentum is in the same direction of angular velocity, or our lowercase omega. So these, again, follow the right-hand rule conventions, in which counterclockwise rotation is positive, clockwise rotation is negative. And it is important to note that angular momentum does change, or will change, because of changes in either inertia or angular velocity. So unlike linear momentum, where linear velocity varies, m is constant in human movement. So in human motion, frequently many limbs are rotating at different angular velocities. So angular momentum of a body is the sum of angular momentum of individual segments. So mathematically, we know that angular momentum, or h, is roughly equivalent to the sum of inertia about a center of gravity of segments times the angular velocity of each segment. So moving to our interpretation of Newton's laws in an angular motion context, angular momentum of an object remains constant unless a net external force acts on it. So in representing Newton's first law, if the inertia of a body, particularly around its center of gravity, is constant, then angular velocity will also remain constant. So for a rigid projectile, gravity is the only external force acting on the body. So the weight acts through the center of gravity, so there is no moment arm around the center of gravity based on the weight of the body. So therefore, weight creates no external torque on a body in projectile motion. In the context of angular momentum, h remains constant unless a net external torque acts on the rotating body. So we can also think of this as conservation of angular momentum. So in this case, mathematically, we know that h initial is ultimately going to equal h final, meaning that the initial moment of inertia times the initial angular velocity is also going to be equal to final moment of inertia times the final angular velocity of a rotating body. So, with the human body being a system of rigid links with a modifiable moment of inertia, and with the law of conservation of momentum, and in this case angular momentum, we can have two different scenarios when it comes to a rotating body. One is we can have an increase in moment of inertia, but there must be a proportional decrease in angular velocity of that rotation. Or we can have a decrease in moment of inertia, where there is a proportional increase in angular velocity of that rotating body. So when it comes to an anatomical or practical example, for a faster spin, if you think about an athlete diving off of a diving board, in order to reduce the moment of inertia, that athlete can tuck or pull their arms in. For a slower spin, you want to increase the moment of inertia, so you would lay out or put your arms out in order to increase that moment of inertia. But in both of these cases, in the first one, we would have a proportional decrease in angular velocity, and then, a proportional increase in angular velocity for a slower spin. With increased moment of inertia, you would obviously have a decrease in angular velocity. Now, when it comes to a body and projectile motion relative to conservation of angular momentum, this angular momentum can stay constant while in a projectile if you don't move segments of the body in an extreme manner. So your initial angular momentum is based off of your initial inertia and angular velocity. So if you reposition one or more segments of the body during this projectile, you have to counter by repositioning one or more segments of the body in the opposite direction to maintain this constant angular momentum about the center of gravity. So, in other words, repositioning one or more of your segments means changing angular velocity of your body about your center of gravity as a projectile. So that's why you would have to have a counteractive reposition of one or more segments in the opposite direction to maintain or conserve that angular momentum as a projectile. A good practical example of this particular scenario is a hurdler. So as this hurdler's leg comes more out front and the opposite leg goes more towards the back, his arms also do a similar pattern. His right leg goes backwards as his right foot comes forward. His left arm comes forward as his left leg goes backwards. So in this way, he is conserving the angular momentum that he has established within his body about his center of gravity by counteracting movement of a couple of segments with his other segments at a very high rate of speed to conserve that angular velocity, conserve his angular momentum and his moment of inertia throughout this track event. In interpreting Newton's second law via the angular interpretation, if a net external torque acts on a body, the body will angularly accelerate in the direction of the net external torque, and its acceleration will be directly proportional to that torque and inversely proportional to its moment of inertia. So this is similar to Newton's second law for linear motion, in which F equals ma. So in Newton's second law, mathematically it would be summed as the sum of torques in an angular motion will be equal to the moment of inertia times the angular acceleration. So the net external torque about axis A is equal to moment of inertia of the object about axis A times the angular acceleration of the object about axis A. So in this case, though, remember that both I and A, so the moment of inertia about that axis and the angular acceleration of the object about that axis, can change or be changed. So for an object to angularly accelerate, that will equal a change in angular momentum, or h. So the change in angular momentum of an object is proportional to the net external torque exerted on it, and the change is in the direction of the net external torque. So torque about axis A and angular velocity about axis A have the same sign, all right? So in this case, angular momentum increases. If torque about axis A and angular velocity about axis A have the opposite sign, then that means that angular momentum about axis A decreases. So if I changes when torque is applied, the change in angular velocity is going to be greater. So the impulse momentum relationship in an angular motion context is mathematically represented by the sum or the average net external torque about axis A, represented by T sub A, times the change in time is equal to H sub F minus H sub I, or the final angular momentum about axis A minus the initial angular momentum about axis A. So if I changes during this change in time, the change in angular velocity is greater of this rotating body. And lastly, in interpreting Newton's third law in an angular concept, for every torque exerted by one object on another, the other object exerts an equal torque back on the first object, but in the opposite direction. So again, it's very similar to Newton's third law, equal and opposite. So the torque on each body is of equal magnitude, not effect. I think that was something that could have been a little bit confusing in the linear interpretation of these laws. So, angular acceleration about axis A is equal to the torque about axis A over the inertia about axis A. So that is all we have for angular kinetics chapter, and we will go over our problem set in class in preparation for our next quiz.